This video was done as part of CSE 145, Ryan's great class where we made this project, and we are the Mangrove team. We're also part of Engineers for Exploration where we do a bunch of other cool stuff, so check us out. Just to go over the people who were involved in this project, I'm Dylan, and I do all of the machine learning portions of the project and a bunch of other random stuff.
I'm Kathy, and I do a lot of the biomass estimation portions of our project.
Hi, I'm Mark, and I'm working with Jeremy on the canopy height estimation.
Oh hey Mark, I'm Jeremy. Plus we've gotten help from a bunch of others.
Huge thanks to everyone at E4E for all of their help and also all of our collaborators for their great help as well. So the first thing that we'll explain is what exactly are mangroves?
Mangroves are a type of tree that grow in coastal areas directly in the salt water. More importantly, they can also take carbon dioxide directly out of the atmosphere at twice the rate of tropical rainforests. And these trees provide valuable ecosystems to many plants and animals. In addition, the area around mangrove ecosystems are beautiful. Unfortunately, prime locations for the destruction of these ecosystems and construction of resorts. Margaritas are fun, but the death of humanity is not. So we need to find ways to conserve mangroves.
In order to mitigate the effects of global warming and extend the time until all the polar ice caps melt, we are tracking statistics about mangroves in order to actually convince policymakers to save mangroves. So this is for politicians in Mexico and abroad. These statistics work really well so far because they're all collected from drones that we use for images and other things. But we do have some errors in how we collect our statistics. For example, our geolocations of mangroves. When we take points of our mangroves, they can be off as much as 10 meters. In addition, when we track the height of mangroves, they can be off a very large amount as well.
I'll first go over the errors in how we measure the canopy height of mangroves. Currently, in our field expeditions, in order to measure the height of an individual tree, we bring a bunch of approximately 1 meter long PVC pipe into the mangroves and stack them up until we think we have reached the top of the canopy.
We can fix this prehistoric method by ditching the PVC pipes for light carbon fiber tubing. We have a sensor pod that has a camera to see the top of the mangroves, and a barometric sensor to measure the height of the mangroves. This method is much lighter and less cumbersome than the previous method, plus with the camera we can actually know where the top of the mangroves are.
Now let's do a quick demo to see how the canopy height system actually works. There we go. This starts with us attaching the sensor pod to the top of the carbon fiber tubing, and then we stack the tubing one on top of another. We can then use the camera to see where the top of the mangroves are, and then use the onboard altimeter to actually see a differential measurement of the altitude from the bottom to the top. In our testing, we only got an error of 0.2 meters, far smaller than what we would have gotten with PVC pipes. Another way that we reduce errors in our measurements is our custom GPS device. Mangrove ecosystems are very wet and muddy and thus require a waterproof, durable form factor that can match this. In the past, rugged hiking GPSs were used, but these devices were terribly inaccurate, giving us errors of over 10 meters in some cases. We could fix this by using survey grid RTK devices, which use a reference location and phase difference between a satellite. But these devices can be even more cumbersome than carrying around a dozen PVC pipes. So let's combine the best of both worlds, a device that is both robust and extremely accurate. So let's go over some of the things necessary. We need a device that is durable, waterproof, has a good battery life, a bright screen, extremely accurate RTK GPS, easy to use UI, is lightweight, is cheap, and is something that we can build in 10 weeks, 6 weeks. So let's put it all together. We need a waterproof case, a Raspberry Pi, a battery, an RTK device, a battery charger, an antenna, and a bunch of SolidWorks magic, and poof, we have our device. ready for researchers to use in the field. So let's actually take this out into the field so we can test it before we glue it all up. So here's our device. So we have directional buttons so you can move the mouse around, a left click, and also backspace. In these USB ports we can upload serial data and in fact get centimeter level resolution. And even without RTK, our device can get sub 3 meter level accuracy for GPS points, which is far greater than what any consumer product can deliver. You can also extend the antenna to reach outside of the canopy, getting even better reception. So in conclusion, we built two devices, a pod that attaches to the end of a lightweight carbon fiber pole that gives scientists an easy to use, accurate method to measure the canopy height of mangroves. In addition, we created a hybrid RTK GPS device that is both extremely accurate and weatherproof to give reliable geolocation of mangroves and really anything else you want. These devices will soon be deployed and still need more detailed documentation on how to use these devices, so please visit our GitHub if you want more detailed technical explanations or further updates on these projects. Thanks for watching!